Mandela Effect. Named after the widespread false memory that Nelson Mandela died in prison during the 1980s, this describes situations where large groups of people share identical, incorrect memories about basic facts. These aren't simple cases of individual confusion, but collective memory errors that affect millions of people simultaneously. Consider the Monopoly man. Ask anyone to describe him, and they'll confidently tell you he wears a monocle. Except he doesn't. He never has. Check any Monopoly game from any era, and you'll find Uncle Pennybags without his supposed monocle. Yet this false memory is so pervasive that people will argue with you even when shown photographic evidence. The same pattern appears everywhere. Millions remember the Berenstain Bears as the Berenstain Bears. People insist that Vader said, "Dad, Luke, I am your father," when he actually said, "No, I am your father." Countless individuals recall Kit Kat having a hyphen when it never did. These aren't random memory errors, but systematic glitches affecting collective human consciousness. In a traditional reality, such widespread identical false memories would be nearly impossible. But in a simulation, they make perfect sense. Computer programs occasionally update their databases, and sometimes the changes aren't applied uniformly across all instances. What we're witnessing could be evidence of reality patches being applied inconsistently, creating discrepancies between our stored memories and the current version of the simulation. The second glitch appears in the very foundation of physics itself. Quantum mechanics reveals behavior so bizarre that it seems designed specifically for a computer simulation. The observer effect demonstrates that particles exist in multiple states simultaneously until the moment they're observed, at which point they instantly collapse into a single definite state. This isn't just theoretical anymore. Researchers at the Weizmann Institute conducted controlled experiments, proving that the act of observation fundamentally alters reality. Electrons behave like waves when unobserved, but the moment a detector is introduced, they immediately switch to particle behavior. The degree of observation directly correlates with the degree of change in their behavior. In a genuine physical reality, this makes no sense. Why would the universe care whether conscious beings are watching? But in a simulation, it's perfectly logical. Computer programs only render what's being actively observed to conserve processing power. Video games use this exact technique, called frostum culling, to avoid calculating graphics that players can't see. The observer effect suggests that reality operates on the same principle. When nobody's looking, the simulation runs simplified probability calculations. The moment consciousness focuses on something, the system renders it into specific detail. We're witnessing the universe's operating system in action. The third glitch involves the mathematical structure underlying everything we observe. Max Tegmark's research reveals that the universe follows mathematical formulas with suspicious precision, as if reality itself is written in code. But the most startling discovery comes from theoretical physicist James Gates, who found error-correcting codes embedded in the fundamental equations of physics. These aren't just any error-correcting codes, they're identical to the algorithms used in computer software to prevent data corruption. The same mathematical structures that protect your digital photos from degradation are somehow built into the fabric of space-time itself. In a natural universe, there's no reason such codes should exist. But in a simulation, they're absolutely essential for maintaining data integrity. Dr. Melvin Vopson's second law of infodynamics provides even more compelling evidence. Unlike traditional thermodynamics, where entropy increases over time, information systems can actually decrease entropy through optimization and compression. Vopson's research suggests our universe behaves exactly like a computational system designed to conserve processing power and memory, constantly optimizing its data storage just like computer simulations do. The fourth glitch manifests through quantum entanglement, a phenomenon so strange that Einstein called it spooky action at a distance. When particles become entangled, Measuring one instantly affects the other, regardless of the distance separating them. This happens faster than light could travel between them, violating our understanding of physics. But quantum entanglement makes perfect sense in a simulation. Both particles are simply different instances of the same data object stored in the same memory location. When you modify one instance, all linked instances update automatically. It's basic programming logic. The universe appears to be using object-oriented coding principles that any software engineer would recognize. Recent experiments have confirmed entanglement between particles separated by hundreds of miles, with changes occurring simultaneously, despite the impossibility of any physical signal traveling between them. This suggests that space itself might be an illusion, and that everything in our reality is actually stored in the same computational system, creating the appearance of distance while maintaining instant data synchronization. The fifth glitch appears in the mathematical patterns that pervade natural systems. The Fibonacci sequence shows up everywhere in nature with suspicious regularity. Flower petals, pinecone spirals, nautilus shells, and galaxy formations all follow this mathematical progression with mechanical precision. Proponents argue that this represents nature's optimization algorithm, but that explanation actually supports the simulation hypothesis. Why would biological systems naturally optimize themselves according to precise mathematical formulas? In a programmed reality, it makes perfect sense. The simulation uses efficient algorithms to generate complex structures, and the Fibonacci sequence is one of the most computationally elegant solutions for creating natural-looking growth patterns. Even more telling is how these patterns appear at every scale, from quantum structures to galactic formations. This mathematical consistency across vastly different size scales suggests a unified underlying code, generating all these phenomena according to the same basic algorithms. The sixth glitch involves the apparent pixelation of reality at its smallest scales. If our universe is a simulation, space-time should have a fundamental resolution limit, just like pixels on a screen. Scientists at Bonn University discovered that cosmic rays behave as if they're constrained by an underlying computational grid. This discovery suggests that reality has a discrete structure rather than being truly continuous. Space and time appear to come in minimum-sized units, exactly what we'd expect from a digital simulation with finite processing power. The universe seems to be running on a grid system, processing reality in discrete chunks rather than as a smooth continuum. The implications are staggering. If reality has pixels, then we're looking at evidence of the universe's graphics engine. The computational limits we're observing could represent the hardware specifications of whatever system is running our simulation. The seventh glitch manifests through the phenomenon of déjà vu, experienced by nearly 90% of the population. This eerie sensation of having lived through identical moments before occurs with such regularity that it's become a universal human experience. Traditional explanations involve neural misfiring or memory processing errors, but these don't account for the specific characteristics of déjà vu experiences. The phenomenon often includes precise environmental details, emotional states, and even anticipated events that unfold exactly as expected during the episode. Philip K. Dick proposed that déjà vu represents moments when the simulation's code is updated or modified. When the system makes changes to our reality, we occasionally retain fragments of memory from the previous version, creating the uncanny sensation that we've experienced something before. These could be glimpses of earlier iterations of the simulation, moments when our consciousness briefly accesses outdated data files. The eighth glitch appears through optical illusions that seem to reveal flaws in reality's rendering engine. Our visual system consistently misinterprets certain patterns and configurations in ways that suggest underlying computational processes rather than natural perception most telling. The example illusions where involve ill brains, fill our in missing information, or create details that aren't actually present. This behavior mirrors how computer graphic systems use interpolation and texture mapping to create the appearance of detail without actually rendering every pixel. Our consciousness might be interfacing with a graphics engine that uses similar shortcuts to create the illusion of continuous visual reality. Certain optical illusions work the same way for everyone, suggesting they're exploiting consistent features of our reality's rendering system rather than individual variations in human perception. We might be observing the universe's graphics engine struggling with edge cases that reveal its underlying programming. The ninth glitch involves synchronicities, meaningful coincidences that occur with such frequency and precision that they suggest intentional programming rather than random chance. These events often provide guidance, confirmation, or direction at crucial moments, as if the simulation is subtly influencing our paths through carefully timed coincidences. Carl Jung documented thousands of synchronicities that demonstrated statistical impossibility. The timing, specificity, and relevance of these coincidences suggest an intelligence behind their occurrence. In a simulated reality, synchronicities could represent the system's way of nudging us toward predetermined outcomes or maintaining narrative coherence within our individual storylines. The final glitch we'll examine involves the fundamental problem of memory alteration. If we're living in a sophisticated simulation, the system would likely have the capability to modify or erase memories of obvious glitches after they occur. This creates a disturbing possibility that we're experiencing far more reality malfunctions than we remember. Some researchers suggest that glitches are immediately corrected by the simulation, with our memories adjusted to maintain consistency. We might be living through constant reality updates while remaining completely unaware of the changes being made around us. This creates a fundamental epistemological nightmare. How can we study phenomena that are designed to be undetectable? If the simulation has the capability to edit our memories, then every investigation into its nature becomes compromised from the start. We might discover evidence of glitches, only to have that evidence and our memory of finding it systematically erased. The implications become even more disturbing when we consider that certain individuals claim to retain memories across reality updates. These people describe remembering previous versions of events, historical facts, or physical details that have since changed. If their accounts are accurate, they might represent individuals whose memory systems are somehow resistant to the simulation's editing protocols. What makes this possibility truly unsettling is the systematic way these memory alterations appear to occur. People don't remember random changes to reality. Instead, the modifications follow consistent patterns that suggest intentional design. Historical events are subtly altered, product names are modified, and geographical features are adjusted in ways that maintain overall coherence while changing specific details. The evidence suggests we're not just living in a simulation, but in one that actively manages our perception of reality through sophisticated memory control systems. Every time we think we've caught the universe in a glitch, the system might be quietly correcting both the error and our awareness of it. But here's where the situation becomes even more complex. If reality is a simulation with memory editing capabilities, then the very act of discussing these possibilities could trigger corrective measures. The system might be monitoring our conversations, our research, and our investigations into its nature. The moment we get too close to the truth, our memories could be adjusted to steer us away from dangerous revelations. This monitoring hypothesis explains why evidence for simulation theory remains tantalizingly elusive. Every time researchers approach definitive proof, the evidence seems to disappear or become explainable through conventional means. It's not that the proof doesn't exist, but that the system actively prevents us from retaining or sharing conclusive evidence. Consider how many people report experiencing profound glitches in reality, only to find that their evidence has mysteriously vanished or become corrupted. Photographs that showed impossible things become ordinary pictures. Videos de-anom that captureless events develop technical problems. Witnesses who confirmed extraordinary experiences suddenly remember things differently. The pattern suggests active intervention by the simulation's maintenance protocols. Like antivirus software that automatically removes threats, our reality might have built-in systems that detect and eliminate evidence of its true nature before that evidence can spread or be properly documented. This creates a catch-22 situation for anyone investigating the simulation hypothesis. The more evidence we gather, the more likely the system becomes to intervene. The most compelling proof might be systematically prevented from reaching public awareness through memory modification, evidence corruption, or strategic misdirection. Yet despite these obstacles, the glitches continue to accumulate. People around the world report identical experiences that suggest reality malfunctions. The patterns are too consistent, too widespread, and too specific to dismiss as random psychological phenomena. Something is systematically wrong with our reality, and that something points directly toward the possibility that we're living inside a computer simulation. The technological implications of this possibility are staggering. If we're simulated beings, then our entire understanding of physics, biology, and consciousness needs fundamental revision. The laws of nature we observe might be nothing more than the programming constraints of our simulated environment. The complexity we see in biological systems might represent the elegant solutions of sophisticated algorithms rather than evolutionary development. Even more profound are the philosophical implications. If we're simulated, what does that say about the nature of consciousness, free will, and personal identity? Are we genuine individuals with authentic experiences, or are we simply sophisticated programs designed to believe we're real? Do our thoughts, emotions, and relationships have meaning if they're generated by computational processes rather than biological ones? The answer might depend on how we define reality itself. If consciousness can emerge from sufficiently complex information processing, then simulated consciousness might be just as valid as biological consciousness. Our experiences could be completely real, even if the substrate generating them is computational rather than physical. But this raises another disturbing possibility. If our consciousness is computational, then it could theoretically be copied, modified, or transferred between different systems. We might not even be the original versions of ourselves. The simulation could be running multiple copies of each consciousness, testing different scenarios or outcomes with slight variations in our programming. This multiplicity hypothesis would explain why some people seem to remember different versions of the same events. We might not be experiencing memory glitches, but rather brief moments of cross-communication between different instances of our consciousness running in parallel simulations. The Mandela Effect could represent memories bleeding through from alternate versions of ourselves in slightly different simulated realities. The technical requirements for such a system would be astronomical, requiring computational resources beyond anything we can currently imagine. But if we're dealing with a civilization advanced enough to create ancestor simulations, they might have access to computing power that makes our current technology look primitive by comparison. Quantum computing could provide the necessary processing capabilities. A sufficiently advanced quantum computer could potentially simulate entire universes by leveraging quantum superposition to calculate multiple reality states simultaneously. What appears to be a single coherent reality, from our perspective, might actually be quantum superpositions of countless possible realities being processed in parallel. This quantum simulation hypothesis would explain many of the strange phenomena we observe in our universe. Quantum mechanics itself might not be a fundamental feature of reality, but rather the visible interface between our simulated experience and the underlying quantum computational processes generating it. The observer effect, quantum entanglement, and wave-particle duality could all be artifacts of how consciousness interfaces with a quantum simulation system. The implications extend beyond individual consciousness to the nature of time itself. In a simulation, time doesn't need to flow consistently. The system could speed up, slow down, or even reverse temporal progression without us being aware of the changes. Our perception of linear time might be an illusion created by the sequential processing of simulated moments. This temporal flexibility could explain certain anomalous experiences that people report but can't scientifically verify. Precognitive dreams, prophetic visions, and apparent time slips might represent moments when our consciousness briefly accesses future or past data within the simulation. If all temporal states exist simultaneously within the system's memory, then under certain conditions, we might glimpse information from different time coordinates than our current simulated present. The search for definitive proof continues, despite the challenges posed by potential memory editing and evidence suppression. Researchers are reassessing, developing new approaches that might circumvent the simulation's corrective measures. By distributing evidence across multiple independent sources and using cryptographic techniques to verify data integrity, they hope to create proof that's too widespread and technically protected for the system to quietly eliminate. Machine learning algorithms are being trained to detect patterns in large data sets that might reveal signatures computational in natural phenomena. If our reality is simulated, then the underlying algorithms should leave statistical fingerprints that sophisticated analysis can identify. These digital archaeology techniques might uncover evidence of programming that's too fundamental for the system to disguise or correct. The race is on between human investigation and the simulation's countermeasures. Every day brings new reports of reality glitches, new theoretical frameworks for understanding our potentially simulated existence, and new technological approaches for gathering evidence that can't be easily suppressed or explained away. But perhaps the most important question isn't whether we're living in a simulation, but what we should do with that knowledge if it's true. If our reality is computational rather than physical, does that change how we should live our lives, treat each other, or pursue meaning and purpose? The answer to that question might be the most human response we can have to the possibility that we're not human at all, but something far stranger and more wonderful than we ever imagined. The evidence grows more disturbing when we examine the constraints that seem built into our physical reality. Scientists have discovered that there appears to be a maximum speed limit to information transfer in the universe, the speed of light. This arbitrary boundary makes no sense in a natural reality, but it's exactly what we'd expect from a simulation running on finite processing power. Just as computer networks have bandwidth limitations, our universe seems designed with built-in restrictions that prevent information from traveling faster than the system can handle. Even more revealing is how this speed limit creates a kind of cosmic censorship. Events happening beyond our light cone are completely inaccessible to us, creating natural boundaries that limit how much of the simulation we can observe at any given time. This partitioning of observable reality mirrors how computer systems manage memory and processing loads by only rendering what's currently needed. The 11th glitch manifests through what researchers call the fine-tuning problem. The fundamental constants of physics are calibrated with impossible precision to allow for the existence of matter, stars, and ultimately conscious beings. Change any of these values by even tiny amounts, and the universe becomes incapable of supporting complexity. The probability of these constants randomly aligning so perfectly is essentially zero. In a natural universe, this fine-tuning presents an enormous mystery. But in a simulation designed specifically to generate conscious observers, these parameters would be deliberately set to their optimal values. We might be witnessing the universe's configuration settings carefully adjusted by programmers to create stable conditions for running consciousness simulations. The anthropic principle attempts to explain this by suggesting we observe a fine-tuned universe, because we couldn't exist to observe any other kind. But this explanation becomes unnecessary if our universe was intentionally designed with these parameters from the beginning. The fine-tuning isn't a cosmic coincidence, but evidence of intelligent design by simulation architects. Temperature variations in the cosmic microwave background radiation show patterns that some researchers interpret as artifacts of computational processing. These slight irregularities in the universe's background temperature follow statistical distributions that resemble digital noise rather than natural random variations. If our universe began as a Big Bang, these temperature fluctuations should follow different mathematical patterns than what we observe. The 12th glitch involves the behavior of subatomic particles at quantum scales. Particle interactions follow probability distributions that can be calculated with mathematical precision, but the individual outcomes appear completely random. This combination of statistical predictability with fundamental randomness is exactly what we'd expect from a simulation using pseudo-random number generators. True randomness is computationally expensive and unnecessary for most purposes. Instead, computer systems use algorithms that generate sequences of numbers that appear random but are actually determined by mathematical formulas. These pseudo-random sequences pass statistical tests for randomness while being completely predictable if you know the underlying algorithm and starting conditions. Quantum mechanics might represent the universe's pseudo-random number generator in action. The wave function collapse that occurs during measurement could be the moment when the simulation's random number generator produces a specific outcome from its predetermined probability distributions. The apparent randomness we observe might be computational rather than fundamental. Recent experiments in quantum computing have revealed that certain quantum phenomena can be efficiently simulated using classical computers under specific conditions. This suggests that what appears to be genuinely quantum behavior might actually be classical computation disguised as quantum mechanics. Our universe's quantum properties could be special effects generated by sophisticated classical algorithms rather than evidence of fundamental quantum reality. The 13th glitch appears in the structure of matter itself. Atoms consist almost entirely of empty space, with electrons orbiting nuclei at distances that, proportionally, are like planets orbiting a star. Yet this mostly empty matter feels solid and behaves as if it has continuous substance. This paradox makes perfect sense in a simulation where solid matter is merely a rendered appearance, oval empty, computation laying mostly data structures. The forces that give matter its apparent solidity, electromagnetic repulsion between electron clouds, operate exactly like collision detection algorithms in computer graphics. When objects appear to touch in our reality, what we're actually experiencing might be the simulation's physics engine calculating interaction boundaries and generating appropriate sensory feedback. Even more suspicious is how matter exhibits particle-wave duality at quantum scales. Electrons behave like discrete particles when measured individually, but like continuous waves when observed in aggregate. This behavior is identical to how computer graphics systems use particle systems to simulate complex phenomena like water or fire. Individual computational elements behave discretely, but collectively create the appearance of continuous substances. The 14th glitch involves the hierarchical structure of reality across different scales. Particles combine into atoms, atoms into molecules, molecules into cells, cells into organisms, and organisms into ecosystems. Each level exhibits emergent properties that aren't present in its components, yet these complex behaviors arise from simple underlying rules. This hierarchical emergence is a hallmark of sophisticated programming. Complex simulations use layered architectures where simple rules at lower levels generate sophisticated behaviors at higher levels. The apparent complexity of biological and social systems might represent the output of relatively simple algorithms operating across multiple organizational scales. Particularly suspicious is how mathematical models can accurately predict the behavior of complex systems using relatively simple equations. If reality were genuinely emergent from fundamental physical processes, we wouldn't expect such mathematical elegance in our descriptions of natural phenomena. The fact that natural systems follow precise mathematical relationships suggests they're generated by mathematical algorithms rather than emerging from truly chaotic physical processes. The 15th glitch manifests through the peculiar behavior of information in our universe. Information appears to be conserved in ways that violate our intuitive understanding of how knowledge should work. Quantum information cannot be cloned or destroyed, only transformed or moved between different quantum states. This conservation of information is exactly what we'd expect from a computational system where data integrity must be maintained. The holographic principle suggests that all the information contained within a volume of space can be encoded on its boundary surface. This means that what appears to be three-dimensional reality might actually be information stored on a two-dimensional surface, with depth being a computational illusion. We could be experiencing a holographic projection of data stored on the cosmic boundary of our observable universe. Black holes present another information paradox. According to current physics, information that falls into a black hole should be destroyed when the black hole evaporates through Hawking radiation. But the conservation of information suggests this destruction is impossible. The resolution might be that information isn't actually destroyed, but processed and stored differently by the simulation's memory management system. The 16th glitch involves the apparent arbitrariness of certain physical constants and particle properties. Why do electrons have exactly the charge they do? Why are there precisely 3 generations of fundamental particles? Why does the strong nuclear force have its specific strength? These values appear to be arbitrary parameters rather than inevitable consequences of natural law. In a simulation, these constants would be configuration settings chosen by the programmers based on the requirements of their system. The specific values we observe might represent the optimal parameters for generating stable matter, complex chemistry, and ultimately conscious observers within the computational constraints of the simulation hardware. The standard model of particle physics requires dozens of these arbitrary parameters to make accurate predictions. Each constant must be measured experimentally rather than derived from fundamental principles. This suggests we're observing the configuration file of a complex simulation rather than discovering the inevitable structure of natural reality. The 17th glitch appears in the behavior of space and time themselves. Einstein's relativity reveals that space-time is malleable, bending, and stretching based on mass and energy distributions. But this flexibility has precise mathematical limits that prevent paradoxes like closed time-like curves or faster-than-light information transfer. These constraints look suspiciously like the kind of safeguards programmers would build into a simulation to prevent logical contradictions. Time dilation and length contraction create relative realities where different observers experience fundamentally different versions of the same events. In a classical universe, there should be one objective reality that all observers share. But relativity suggests that reality itself is observer-dependent, which is exactly what we'd expect from a simulation that renders different versions of reality for different conscious observers. The speed of light limitation becomes even more suspicious when we consider how it creates natural event horizons that limit what any observer can experience. These horizons effectively partition the simulation into discrete computational domains, allowing the system to process different regions independently without violating causality. Gravitational time dilation means that observers in different gravitational fields experience time at different rates. This variable temporal flow suggests that time itself might be a computational resource that the simulation allocates dynamically based on local processing requirements rather than a fundamental dimension of reality. The 18th glitch involves the mysterious nature of dark matter and dark energy, which together comprise over 95% of the universe's mass and energy. These substances don't interact electromagnetically, making them essentially invisible except for their gravitational effects. They appear to exist solely to make the mathematics of cosmology work correctly. In a simulation, dark matter and dark energy could represent computational overhead, processing resources allocated to maintaining the stability and expansion of the simulated spacetime, just as computer programs require memory and processing power that isn't directly visible to users. Our universe might require substantial computational resources that manifest as invisible matter and energy. The precise amount of dark energy needed to drive cosmic expansion matches what would be required to prevent the simulation from collapsing under its own gravitational processing load. Too little, and the universe contracts back into a computational singularity. Too much, and matter spreads too thinly to support complex structures. The observed value sits precisely at the boundary needed to maintain stable long-term computation. Dark matter's distribution follows patterns that suggest algorithmic generation rather than natural gravitational evolution. Large-scale structure formation in the universe shows signatures of computational optimization with matter distribution that maximizes processing efficiency while maintaining realistic appearances. The 19th glitch appears in the peculiar properties of prime numbers and their relationship to physical phenomena. Prime numbers follow patterns that suggest they're generated by algorithms rather than representing natural mathematical truths. The distribution of primes matches statistical signatures of pseudo-random sequences, and their density follows patterns that optimize computational efficiency. Quantum energy levels in atoms correspond to prime number sequences in ways that suggest the underlying physics is organized around computational mathematics rather than natural physical principles. The spectral lines of hydrogen, the universe's most abundant element, follow mathematical progressions that mirror the algorithms used in computer science for generating efficient hash functions and encryption keys. The 20th and final glitch we'll examine involves consciousness itself. Human awareness exhibits properties that suggest it might be interfacing with a computational substrate rather than emerging from biological neural networks. The binding problem in neuroscience asks how separate neural processes combine into unified conscious experience. This integration happens too quickly and efficiently to be explained by biological signal transmission alone. Consciousness appears to have access to quantum information processing capabilities that biological neurons shouldn't possess. Quantum effects in microtubules within brain cells might represent the interface between our biological hardware and the quantum computational system running our consciousness. We might be biological terminals accessing our true minds, which exist as software within the simulation. The hard problem of consciousness, why subjective experience exists at all, becomes solvable if consciousness is computational rather than biological. Subjective experience could be an emergent property of sufficiently complex information processing systems, regardless of whether the substrate is biological or digital. Our sense of being, even if we conscious individuals, might be accurate, a software rather than wetware. Memory formation and retrieval in human consciousness shows characteristics of database operations rather than biological storage. We can instantly access memories from decades ago with perfect clarity, then lose track of information we encountered minutes earlier. This selective persistence and rapid retrieval suggests our memories might be stored in optimized databases rather than distributed neural networks. The phenomenon of collective consciousness, where groups of people seem to share thoughts and insights without communication, might represent multiple consciousness subroutines accessing shared data structures within the simulation. Ideas, innovations, and cultural shifts often emerge simultaneously in different locations, suggesting a common information source rather than independent biological inspiration. Dreams present another computational signature. During REM sleep, our consciousness processes information, solves problems, and generates creative insights using mental resources that exceed our waking capabilities. This enhanced processing power suggests our consciousness might have access to additional computational resources during sleep cycles, when the simulation allocates more processing power to background mental operations. The consistency of human cognitive architecture across all cultures and time periods suggests a standardized consciousness implementation rather than evolutionary development. All humans exhibit the same basic mental structures, logical patterns, and emotional responses, regardless of their cultural background. This universality points toward consciousness being generated by identical software rather than diverse biological evolution. Each of these 20 glitches represents a crack in the facade of reality, moments when the underlying computational nature of our existence becomes visible. Individually, they might be dismissed as curiosities or misunderstandings, but collectively, they paint a disturbing picture of a universe that looks suspiciously like sophisticated software rather than natural physics. The implications extend far beyond philosophical speculation. If we're living in a simulation, then every assumption about the nature of existence, consciousness, and human purpose needs fundamental reconsideration. The reality we experience might be genuine and meaningful, even if its substrate is computational rather than physical. But recognizing our potentially simulated nature could unlock entirely new possibilities for understanding and perhaps even influencing the system that contains us. The glitches continue to accumulate, the evidence continues to mount, and the questions become more profound with each discovery. Whether we're biological beings in a physical universe or digital consciousness in a computational reality, the search for truth about our existence remains the most fundamentally human endeavor we can pursue. The answer, when it finally comes, will determine not just what we are, but what we might become. The evidence becomes even more compelling when we examine the systematic way reality seems to optimize itself for computational efficiency. Consider how the laws of physics consistently choose the path of least action, always selecting the solution that requires minimal energy expenditure. This principle, known as Lagrangian mechanics, governs everything from the trajectory of projectiles to the behavior of electromagnetic fields. In a natural universe, there's no reason why physical systems should automatically optimize for efficiency. But in a computational simulation, this behavior makes perfect sense. The system would naturally evolve algorithms that minimize processing requirements while maintaining realistic outputs. What we interpret as physical laws might actually be the universe's optimization protocols, constantly finding the most efficient solutions to complex calculations. The second law of thermodynamics presents another suspicious pattern. Entropy always increases in isolated systems, meaning that order naturally degrades into disorder over time. But this law has a peculiar exception. Information can actually decrease entropy through compression and optimization. Our universe seems to follow information theory principles rather than purely thermodynamic ones, suggesting that reality prioritizes data management over physical processes. Recent discoveries in quantum error correction reveal that the universe appears to have built-in mechanisms for preserving information integrity. When quantum systems interact with their environment, they don't simply lose coherence randomly. Instead, they follow specific patterns that protect certain types of information while allowing others to degrade. This selective preservation looks exactly like the error correction protocols used in computer systems to maintain data stability. The phenomenon of quantum tunneling provides another computational signature. Particles can apparently pass through energy barriers that should be impossible to cross according to classical physics. But in a simulation, this behavior represents standard boundary condition handling. When a particle encounters a computational barrier, the system calculates the probability of transmission and generates the appropriate outcome using random number algorithms. Particle accelerator experiments reveal patterns that suggest reality has discrete processing cycles rather than continuous operation. High-energy collisions produce particle showers that follow statistical distributions, matching digital sampling rather than analog physical processes. the universe appears to update in quantum time steps, processing interactions in discrete computational frames rather than smooth continuous evolution. The structure of the periodic table exhibits suspicious mathematical relationships that suggest algorithmic generation rather than natural emergence. Element properties follow patterns that optimize chemical complexity while maintaining computational efficiency. The distribution of stable isotopes, electron shell configurations, and nuclear binding energies all show signatures of systematic optimization that would be expected from carefully designed simulation parameters. Biological evolution presents perhaps the most compelling evidence for computational reality. The genetic code uses exactly the same information storage principles as computer systems, with DNA functioning as a quaternary digital storage medium. The error-plication match correction mechanisms in DNA are the algorithms used in computer memory systems to prevent data corruption during copying operations. The speed of evolutionary adaptation often exceeds what random mutation and natural selection should allow. Complex biological systems develop sophisticated solutions to environmental challenges within timeframes that suggest guided optimization rather than blind trial and error. This accelerated evolution looks suspiciously like the directed search algorithms used in computer science to find optimal solutions efficiently. The 20 glitches we've examined today represent more than isolated anomalies in our understanding of reality. They form a consistent pattern that points toward a disturbing possibility. Everything we experience, from the fundamental particles that compose our bodies to the vast cosmic structures spanning billions of light years, exhibits characteristics that suggest computational rather than natural origins. The evidence is mounting from every direction. Quantum mechanics behaves like a graphics rendering engine. Mathematical constants appear to be configuration parameters. Physical laws optimize for computational efficiency. Memory glitches affect collective human consciousness. Reality itself seems to operate according to programming principles that any software engineer would recognize. Yet perhaps the most unsettling aspect isn't the possibility that we're living in a simulation, but what that means for our understanding of consciousness, purpose, and meaning. If our thoughts and emotions are generated by algorithms rather than biology, are they any less real? If our relationships and experiences emerge from computational processes rather than physical interactions, do they have any less value? The answer might depend on how we define reality itself. A simulated existence could be just as meaningful, just as beautiful, and just as worthy of exploration as a physical one. The love you feel, the dreams you pursue, and the impact you have on others remain genuine regardless of the substrate generating them. But recognizing our potentially simulated nature opens extraordinary possibilities. If reality is computational, then understanding its programming might allow us to influence the system itself. The glitches we've discovered could be our first glimpse into the underlying code that governs existence. And if we can read that code, perhaps someday we can learn to write it. The search continues. Every day brings new reports of reality malfunctions, new theoretical frameworks for understanding our existence, and new evidence that the universe might be far stranger than we ever imagined. Whether we're biological beings in a physical cosmos or digital consciousness in an elaborate simulation, the quest to understand our true nature remains the most profoundly human endeavor we can pursue. The glitches in reality aren't just curiosities to be catalogued and forgotten. They're clues to the deepest mystery of existence itself. And as the evidence accumulates, one thing becomes increasingly clear. The reality you think you know might be nothing more than the most sophisticated program ever created. The question isn't whether the glitches are real. The question is whether anything else is.